So Radek, look.
Yes, Luboš. Yes.
Something is going on here. Something real, right?
It seems we are live, right?
We are live. We are live. Yes, we are live. So we are going to make it. We did it again,
Yeah, long
and
time we haven't seen, right? On webinar. Do you
yes,
remember
yes,
when the
for
last
quite a
webinar
while.
took
Yes,
place?
yes, we have free webinars in like in summer or before summer, slightly before summer,
Yeah, yeah.
to show things really in detail, right? So it's like 6 hours of videos on our YouTube channel, so everyone
Hmm.
can take a look. And yeah, so this is the new release webinar, and I think we will start very soon. Actually, on my clock it's 2 p.m. So
Yes.
actually it's time. So do we wait? Do we start?
I think we can start, I guess. Yeah.
Okay,
It's
we will
30
start.
seconds after 2. So let's go
Okay,
for it.
we'll make it. We'll make it. Okay, finally. So I need to do something. Yes, I need to share my screen. Well, okay.
Okay,
So I'll
but
start.
I think we can see it. We can see it. Yes.
Okay, you can see it. We
Yes, I
can
can
see it.
see the
Okay,
presentation
okay,
first slide.
okay, perfect. So yes. Hello everyone. This is Luboš Pirkl from CFD Support, and I would like to welcome you to another webinar. It's number 95, and today we would like to show you what we did. Again, yes, here's the new version of TCAE. It's version 25.10, and we would like to show you what we did, and we would like to share with you our thoughts and new features and first ideas. So make yourself comfortable and have a look what we did. Prepare your questions. At the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. Use your time to the fullest. So ask your questions anytime during the webinar, and we are ready to answer them. And we'll be happy to answer them. So ask about anything. We will do our best. So there will be Q&A. That's important. The webinar is being recorded, and the recording will be made later publicly available on our YouTube channel. So yes, there will be a recording. It's a typical question and fair question, of course. And yeah, so it's me, and together with me on the line is my colleague Radek. So let's check Radek. So knock, Radek, are you with us?
Yes, I am. Hello, Luboš, and hello to the audience. Everything seems to be ready, right?
Right.
All of us in
So
good shape after summer.
yes,
So
yes. Very well. Everything is well, and I think we can start. Okay,
yes,
so
let's
let's
go.
start. So yes, we did it again. We have again spent enormous time, enormous effort on the new version, countless sleepless nights and sleepless days. We created the new version, which is yeah, quite a lot of work, by the way. So let's talk about it. And in this webinar, we will present what we think is important about it. So here's the agenda of this webinar. So in the beginning, there will be a necessary introduction, but because not everyone is familiar what's who we are and what's on the table, then there will be a couple of general thoughts about the new version. I will also share a couple of thoughts about our future developments. Then Radek will definitely come with the technical part, and he will explain the new features of new TCAE version a little bit more in detail. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free. Again, I would like to ask you to ask your questions, and we will do our best to answer them, and it propels us forward for sure. So that would be it. So it sounds like a plan. So let's go to execute it. Yeah, maybe it's time, Radek. We will perhaps we will switch the cameras off
Okay.
because it will give a better screen ratio to the audience. So I
Perfect.
hope,
Yeah.
yeah, we're gone now, but we're still here actually, and and we'll do our best. So
Yeah, we
okay,
appear
so
again at the end, right?
yes, let's do that. Let's do that. Let's come back to Q&A with our cameras
Perfect.
again. Okay, so CFD Support is a company. We are located in Prague, Czech Republic. We are founded in 2009, which is quite a lot of time. We are dealing with engineering simulations for a while. So we are dealing specifically with CFD, computational fluid dynamics. Quite a little bit we are dealing with FEA and FSI. We do quite a lot of optimization and also acoustics. We have, yeah, we provide consultancy and services, and we are delivering complete projects. But of course, the main product of us is simulation software, which is called TCAE. TCAE is a comprehensive simulation environment where the users can simulate fluid dynamics and related tasks. So that's TCAE, and we will introduce you the new version today. But let me first note a couple of important notes. So now I will say what I think is important about TCAE, which is TCAE. It consists of software modules. Not everyone needs everything, but all of them can be used, or just one of them can be used. So this TCAE is a set of software modules, and every engineer, every user can pick or choose the relevant software modules that work for him or her. So that's important. So there are software modules. There is a module for meshing, for example. There is a module for fluid dynamics, for finite elements. There is a module for acoustics. There is a module for optimization, and some other modules are already in progress. So it's always up to the user what module is used. That's important. And there are a couple of principles we follow with the software. It's our philosophy, and we follow these principles to that, I would say. So I will now speak about those principles. So TCA is flexible. Flexibility is extremely important for us. So we believe that every engineering, I would say, department is specific. There are specific, I would say, habits. There are specific specific experience. There are specific tools, historical development, and everything. So we are extremely flexible. TCAE is flexible, and it's possible to be used in different ways. It can be used by a single user. It can be used by multiple users. It can be run inside another software, or it can run another software. It's ready for modern workflows, and yeah, it's extremely flexible. It works with other open source pieces. It works together with in-house codes. It works perfectly with commercial codes. It's really ready to help and to be used in a way that is necessary and that is appropriate to users' skills, users' resources, users' ways of work. So it's flexible. It's unlimited. It means that there's yes, we license it because we have to make for a living from something. So there are licenses, but the license is provided to a single organization, and there are no limitations on number of its users, jobs, cores, sessions, hardware installations, anything. So basically, the users, the client can use their resources to the fullest. So it can be run on a multiple software or anything. So for this it's really unique. It's definitely focused. It's clearly focused on specific applications. TCA is very much focused on turbo machinery applications and external aerodynamics applications. So it's not a general purpose code. It's it's, I would say, specific code or specific software which is focused on specific applications, and that allows it to be accurate. We are obsessed with accuracy. We believe that accuracy comes with focus and understanding what's going on. It comes with skills, it comes with experience, patience, and dedication. So yes, it costs you a lot, and the software only can be accurate if it's focused and if it's perfectly prepared. TCAE is automated. So we believe in automation very much because we believe what's automated is extremely effective. So we automate anything what is possible, and we develop TCAE to be as much automatable as possible. So it can be used by I would say non-experts who just put the data in and pull the data off. It can be used as a black box, or on the other hand, it can be used for research. It can be used for large projects because the source code is open, and it can be used for really sophisticated, I would say, high-end workflows where the details matter. And the beauty of it is that it's the user who decides how deep to dive into the rabbit hole, or not at all, actually. So it's automated, and automation is everywhere in TCAE, and it's developed in mindset of automation first. TCAE can be used in very wide range of using ways. So it means it can be used remotely. It can be used in a unique client server option. So it can be used remotely from home to office, or from office to home. It can be used on laptops, desktops, clusters, clouds, pretty much everywhere. It's ready for that. It's been shown many times, proven many times, and we are ready to prove it again together with you. So there is very wide range of options. Of course, it's developed natively for Windows. It's developed natively for Linux. It has graphical interface. It has batch mode, and the workflow is very consistent and very well tested. Yes, it's been definitely very well tested. We did really many benchmarks in the past. We have 15 public benchmarks that can be repeated anytime. They are public, so anyone can basically run them, download them from a website and run them. So this is the proof it works and it's accurate. We have more than 50 tutorials available on our website, so users can download more than 50 tutorials and run them again and learn with them and build new, based on them, can build new projects and everything. So there is a lot of content available, and also our technical support is good because we value our clients and value our users, and we help them and we work in a so I would say a familiar environment together with our users, and we believe that that's a good way to enjoy what we do. TCAE is based on open source. It means that it's built on open source pieces, because here at CFD Support we have mastered the process to learn open source, integrate it into the TCAE, and provide, based on open source, we are providing professional tools that can be used for real industrial projects. That's very important. There is more than 60 open source projects, and we maintain and update them all regularly. So you can imagine how much effort it takes to put it in one comprehensive package, which works. And on top of these open source pieces, we have invested and spent more than 50 man-years of development here in a group of a couple of PhDs who consistently develop these open sources to deliver TCAE as it is. So that means we have spent enormous time and effort to make out of open source something which is usable in the real industrial practice, and that's really important, and that's the core information of all of it, basically, I would say. Yeah. Okay, so today we are coming with the new release. It's 25.10. which is again so much better than anything what we released before, because yes, we have removed more than maybe or about 100 bugs that are everywhere, because creating software is in fact really difficult, because you have to be prepared for endless endless variants of options from various users in various conditions for various projects. So it really is difficult to create it and maintain it and support it. So believe me, we have spent yeah, a lot of effort. We have fixed more than 100 bugs, and on top of that, we have created quite some appealing new features. This release is quite a lot about turbulence. So we have about turbulence modeling. So we have extensively tested and created LES simulation models. So we have integrated whale turbulence model, which is LES model, and a couple of other turbulent supporting features. So that's certainly a couple of those I would like to mention. Then we have I'm talking here only in general, and Radek will share more details. But this is just a little taste of what we did. So we did a couple of very useful workflow enhancements, like for example automated number of course selection or automated internal point selection, and few others. So I will not mention all of them. You can find them in the news section on our website, the whole list of what has been done, and also it's in the new version of TCAE manual if you would be interested in all the details. And I will go ahead a little bit in this presentation. So I would like to share a couple of thoughts about the future development, because as you know, we are always in a move. We are always in a spin. So we are developing the tools already. So we are typically working or developing several branches, and when we are already now developing the new version for the next year. So I hope it goes without saying that we will be focused on turbo machinery and external aerodynamics. And on top of that, we will specifically keep developing the optimization module, because we believe optimization is the future, because we have to iterate towards the best possible, not just run random simulations, but we want to move in a specific space, which is parametric space, which is huge. And for that, we need special methods, which is optimization methods, which based on simulation results help us to move towards our goals. So optimization is definitely a really big topic, and we will keep dealing with it for the future. We definitely will dedicate a lot of our best research time to acoustics, because acoustics is something which is really advanced, and not everyone can do that. So we will keep our eye and keep focusing on acoustic simulations for the future. So these two are really important. We also have a passion for biological flows, especially blood flows. So these biological flows and blood flows will be in the future, quite researched in our company too. We are going to deal with them, or we are dealing, or going to even more deal with hemolysis and with rheological models like shear thinning properties of blood, for example. Also the viscoelasticity and a little bit of chemistry, and based on these specifics of blood, we will be optimizing blood pumps. So definitely biological flows are something what we are going to keep working on. Then we are working on the new software module, which is called T-Base. So it will allow every user, which is really important. So every user will be able to store the results in the large databases, keep them for the future, and based on those data, it will be possible to run machine learning and AI and specifically create surrogate models to give answers in seconds instead of hours or days. So T-Base is very, very much advanced already. And I mean, the development, it's in the advanced phase. We are testing it currently, and we will very likely release it soon. Which brings me to the what will be the next release. So the next release is scheduled to spring 2026, and it will be huge because there will be new OpenFOAM update based on openfoam.org, plus the best things available across the OpenFOAM community, plus those other 50 many years spent on the open source. So really big update because everything will be updated to the latest version, and it's a relatively it's a quite big deal. There will be the T-Base, so the first T-Base version will be released next year, and it will be the kickoff year of practically new software, which will be revolutionary, because not only that we will develop it, but we will give it in hands of our users. That's important. So it's not being hide anywhere. It will be given into the hands of our users. It's important, and that's the real democratization of software, because every user will be available or be able to save his result, their results, and use them, and use AI and everything. So that's what we are going to do, and it's coming. There will be, of course, version updates next year, and many more. And of course, we are for our users. We are following all the big trends. Of course, AI and machine learning is a mega trend of these days and years and months. And we are closely following it, and we can be sure that we will pick the best of what's available for our software. It seems that AI agents might help not only with the data treatment, but and surrogate models. They will very likely do a lot of work for us. They will very likely preset cases for us. So we're also very closely following, and we will bring it when we feel it brings the value for our users. We will bring them and implement them in our software. Of course, we will keep eye always on automation. It's our I would say it's our first priority. Automation is everywhere. GPU is quite big trend. We are following it. It seems to be quite good on very big repeatable cases. It's worse for research. It's not good for small cases. That's what we have found so far. Lattice Boltzmann is also a question we're closely following. Quantum computing is also a big trend. We are also following. Let's see. No one knows at the moment. And there are a couple of others. So we are closely following, and you can be absolutely sure that we will put it into the software in the right time. We're on the pace of time. Okay, Achtung. It seems that there's an expert waiting on the air. So let's take a look. So knock, Radek again. Are you following? Yeah. Are you going for it?
Yes, I were following. So perfectly said the first part of the webinar.
That's great.
And I will just continue with a more detailed description of the new features, utilities, etc. So
yes, that's really great. So if I ever will find how to switch the presentation over to you, if I ever well, there's new graphical interface in this, and I'm well, this is me, and well. Okay, so yeah, it's a little bit embarrassing, I would say, but I do not know what to. Oh, okay, I see Radek is here, and if I click, no, yes, Yes, yes.
Make a presenter. Okay.
GIF, no, it's just you make a presenter. Okay, make a presenter. Okay, so I got it. I have it. I have it. So yeah, sorry for this. Sorry for this. I promise I will learn it for the next webinar.
All
So
right.
Radek, the stage is yours. And one last note, I would like again, I would like to ask the audience, ask your questions, ask about anything. If you have any questions deep in your mind anywhere, just ask. As you know, there are no stupid questions. There are only stupid answers. So don't worry. Ask your questions,
It's on
and
us.
we will be it will we will be happy to answer them. So yeah, this is it from me. And Radek, yeah, the stage is yours.
Okay, thank you, Luboš. So welcome again, and I will directly dive into the particular features we have implemented. And besides of these features which are visible for the user, we made dozens, as up to hundreds, small code fixes, functionality fixes, and the other stuff which which helps the project to be more robust, more stable, more user friendly. So this is the list I got from my colleague Prokop, which picked the main merges in our repository, code repository, and I picked the most visible ones, and I created a short presentation to present these several features which we bring into the new version of TCAE. So this is the short list. Let's say there are just few small cosmetic changes in the layout. Uh, there are new functionalities for the T-Mesh. The main functionalities are that the internal point now can be automatically set. So there are no boring stuff like looking for the point which lies inside the domain or inside a component you want to mesh. So this is really nice feature. Uh, Mesh quality fields are also visualized or can be computed and visualized. Another one, if you don't need to bore about or look for how many cores your computer has, there is new automated function which just reads the system information about the physical cores and automatically sets all the cores for the simulation if you want. Then there are a bunch of new features uh, connecting or touching the turbulence modeling. So one of it is the decaying version of Omega turbulence models. Then we implicitly bring the LES modeling, so no need to enable it via the scripting. So now there you can find implicit you can find LES model. We started with the wall adaptive uh, version of LES turbulence modeling. Connecting the LES modeling, we also implement like index, which can show you the main parameters or uh, uh, the main index, which show you the quality of the resolution connecting with LES, if the mesh is well resolved or not, or if it's still modeling. Then for LES, we have implemented basic turbulent velocity inlet, so really to generate the real fluctuation of the velocity. Connect because of the turbulence modeling and the LES, which requires higher order schemes. So we added options to pick directly from the GUI new discretization schemes, and we still working on the acoustic module, and there is re-implemented and optimized the algorithm for acoustic signal processing, and for the TOPT, not TCAE, for the TOPT we added the implicit option to use the Dakota Ego algorithm. So if you so this brings the connection with Dakota and with the particular algorithm. And last but not least, as Luboš pointed, we are playing with the blood pumps. So I have an example of the Excel blood pump tutorial. All right, so let's start with the cosmetic changes. So you don't need to be scared if you see the GUI layout for the first time. We are put out some buttons from the others options to be directly visible on the main panel, like these restore and purge buttons. Restore is just for restoring the case to the preset preset moment, and uh, which is ready to bring the project ready for simulation from the plain start. The purge is the button when, for example, you would like to share the project with someone for support to send to us, or we just want to keep just the setup and get rid of all non-necessary files like results, etc., for the later usage and to save some storage on the disk. So this is just a smaller and cosmetic changes in the layout. But now let's go for the nice features which brings new options for the user. So the first one is the automatic internal point. So now you don't need to care about the internal point. For those who are not familiar with creating the simulation domain and the meshing part, typically the mesh consists of the mesh is created using the external geometry in the STL format. And typically, if you are using the internal flows, you build the geometry from the components, so parts which are connected next to each other, and each part is meshed separately. And because of the nature of SnappyX meshing, so you need to have some background mesh, and you need to know which part of your closed domain will be meshed, if inside or outside. So in the previous version, you needed to put this internal point manually. So in the GUI, you need to place the point into proper position, and then the coordinates were filled automatically. But now you can use the automatic internal point, and this point is evaluated with the internal algorithm on the fly. So then you just need to check this option, and you don't need to take care about placing the point correctly. If in case you have really complex non-standard geometry, so it may happen that the automatic internal point evaluation fail, so then you still can place manually the point to the correct place. Just for checking, there is this internal point which is evaluated during the simulation, so during the meshing, can be found in the tmesh module, so within the project for each component, and there is a new file internal point which is then included into the SnappyX mesh dictionary. So pretty simple and pretty useful. Then we are still in the tmesh. So now there is the option to evaluate the mesh quality parameters instead of fields, which visualize the particle parameter like non-orthogonality, skewness, cell ratios, uh, and other. And you can easily enable it by clicking in the general in the section tmesh. So clicking on write mesh quality fields, and whenever any component is meshed successfully, you can visualize the mesh, and automatically within the mesh there are several fields which you can visualize. So maybe here I can show an example. So I loaded the simple pipe tutorial, and I will maybe here I can show you, for example, this automatic internal point. So as you see, just need to click here. If it's not, I think now for the new case it's in default, I guess. So you can keep it in this way, and you don't need to take care about placing the internal point inside your component. And let's go click on the meshing. So let's go to the manager. I will click mesh all, and now the meshing will start it. Okay, but first because I made some changes, so I need to first apply these changes, and now I can click mesh all. So now the meshing is done, and I think it will be it's not done is is doing, and when it is done, okay, I can click here show component. I can get rid, so now in the pipeline browser I need to visualize it. So this CFD mesh, I will get rid of CFD geometry, and as you can see now there are several fields to be visualized. So here you see these are the main parameters, the quality parameters of the mesh. So typically non-ortho angle visualization. So for bed meshes, you can nicely locate the bed non-orthogonality playset and try to, for example, remesh it, or maybe it's connected to the bed geometry quality or sharp edges. So then you can redesign the geometry and try to remesh the component and see if it helps, if you reach less non-orthogonality, etc. So you can play with this visualization as you want. So for example, if you would like to see the given non-ortho cells, so you can, for example, apply the threshold. You can choose the given parameters. So for example, this non-ortho angle, and now okay, I would like to see all the angles, all the cells which has non-orthogonality higher than 40. So this is in degrees, and now you can see all the cells having the non-orthogonality larger than your threshold. So here maximum is 55, which is pretty nice mesh from the non-orthogonality point of view. In the same way, you can visualize the other ones, aspect ratio. So the aspect ratio of the cells, cell volume ratio or cell volume itself. So the sizes of the cells. Cell volume ratio, for example, is the minimum ratio of the neighboring cells to the given cell, etc. If you would like to see the list of all of them or any other explanation, so you can go to our web pages, to the documentation, open the manual, and for example, I'm not sure what this cell volume ratio is, so I will type cell volume ratio. Okay, if I type it correctly, it should be found. Yes. So the cell volume ratio is the minimum ratio of a cell's volume to that of its neighboring cells. Yeah, and here are the explanation of all these parameters. So I think this is a very nice feature, mainly for tuning the mesh to the best possible quality. So in this way, you can really nicely play and visualize what you need. So this was the mesh quality fields. So only you need to do is check these right mesh quality fields, because it takes some time to evaluate them. And if you, for example, go for the optimization or some repetitive work, so you are able to uncheck it just to speed up the whole process. So therefore, it's on demand and not automatically evaluated. Then new feature, use all local cores functionality, which is small feature but pretty useful. So in default, now if you go for the tmesh or TCFD module where the number of processors is set, so either you can set your number of processors you would like to need if you don't want to use all physical cores, or if you set to 0, so it will automatically use all local cores. So it will just check the system properties, found how many physical cores is available, and automatically set this number for the simulation. It is connected to the local core, so it's not connected to the nodes or some clusters. So it's always connected to the node from which the TCAE was run. All right, so all local cores functionality, also pretty useful. Then we are coming to the turbulence modeling. So we have request, and we see the importance of the proper turbulence quantities modeling, typically for external flows. So you can imagine if you do the external flows like airfoils or any other, so you make your domain big enough to get rid of the influence of boundary conditions and boundaries. But if you make the domain pretty large and you keep the standard set up for k omega quantities, so there is huge dissipation because of the omega dissipation of internal energy, and basically you typically know what are the proper values to be used for the simulation near your body, not far from your body or far from your object. So one option is to somehow apply some set fields and keep some values in the half of the domain before your object at the chosen value, or we implemented more clever options. So this is the non-decaying k omega turbulence model, which basically keeps the minimum, so keeps the value at the inlet within the domain. So pretty simple to explain. So basically the turbulence equations are equipped with a new decay control guy, which eliminates the effect of the dissipation. So it just keep the values of k and omega at some infimum or minimum values, which is set in the given dictionary, and TCAE sets it automatically to the value of conditions at the inlet. So basically the decay control modification lies in this in this guy, and similarly for the omega equation, the omega equation is equipped also with this decay control guy. What is the effect? So for example, if you are simulating airfoil external aerodynamics, so typically standard way is to have 100 times the domain should be 100 times larger than the span of the airfoil or span of the cord. So basically the domain is pretty large, hundreds of meters if you have 1 meter airfoil. And if you set a standard k omega turbulence model and you say some value at the inlet k, for example here 0.5 and omega to 10, which is pretty low omega, so then you can still see some decaying of these values, and basically just before your object there are totally different values than you are set for the simulation. And even if you set, if the omega is larger, which typically is, then typically the turbulence intensity or kinetic energy is pretty low, and it doesn't follow, for example, the definition of the simulation or of the problem. So if you basically enable, there is just one button, options, choose on enable or disable this decay control. So if you enable the decay control, then you will see that the inlet values are kept throughout the domain, and as an outcome, you really have the proper turbulence quantity values near your object. So you are simulating what you really wanted to simulate. So this is the decay control. Just to show you, it's pretty simple. Really, you go to the physics, to the turbulence modeling, and just one button click, and you have it enabled. So this is the non-decaying k-omega turbulence modeling. Then we implicitly offer the usage of LES turbulence model. Particularly, we started with the wall adapting local area viscosity turbulence model. Again, to enable it, it's pretty simple. You just choose this model. If, for example, it's just for transient simulation, the LES. So if I go to the time management, I enable the transient simulation, and if I going back now, we have the whale option for whale turbulence model to be used as a turbulence modeling with just 2 parameter standard LES delta coefficients for the subgrid scale modeling, and turbulence Prandtl number for boundary conditions, maybe mainly. Okay, so going back, so this is it. Of course, the importance of the mesh refinement is pretty high. Of course, you can enable and run it on even on the rough mesh, but of course the accuracy and the results will not correspond to the expected values. But there are basically no limitations. The only limitation is that you need to really use highly resolved mesh to get accurate result. But the setup is pretty straightforward. Okay, connected with the LES models, we implemented these less IQ coefficients, which can show you if the resolution of the mesh in the volume is okay or not. And this is the simple rule which compares the values of the resolved turbulent kinetic energy, so the resolved by the grid, and the kinetic energy which should be modeled by the subgrid model. And this proportion should be close to 1. So if there are no modeling, the value should be 1. So this is the first, let's say, check if your mesh is resolved properly and your result has chance to be accurate, and you are basically running the LES mode and not only some modeling. So the appropriate values, it's said that should be higher than 0.8, so 80, at least 80% of the kinetic energy should be resolved, and typically you would like to see a value 1 everywhere. So if I show you how it looks, so I run a simple example on external flow on a simple shape like a cube. And if you visualize a less IQ field, then you will see something like this. So mainly some kind of vortices which has a small scale should be modeled, and some, for example, here interesting part just before the obstacle. And when you try to resolve the box, so I just resolve in the neighborhood of the box and the small wake area, so then you can see that this index shows better values, so there are smaller and less red areas for the finer mesh. While of course in the still rough mesh, you will see big area which are based on this index not well resolved. And if you would like to compute it, it's pretty simple. It's done automatically. So if I'm here, so what you need is to just check here in the runtime rate quantities to compute average quantities, to write average velocity, because it's just some fluctuation of the velocity to evaluate properly these indices. And then at the end, you will see the field LSIQ, which can be visualized. I have no results here, but basically it's pretty straightforward. Like you visualize velocity at the end of the simulation, in the same way you can visualize this coefficient. So this was the index of resolution. And last option is the turbulent velocity inlet condition. So when we are going into the LES field, we would like to also see the real fluctuation of the velocity, not just the model by the k omega like for the runs models, but here we would like to make some real oscillation in velocity. So it uses pretty simple boundary condition, which is called turbulent inlet velocity, which just adds the random component to the mean field. Yeah, and the parameters are basically, so the reference velocity, basically the velocity at the inlet, and the fluctuation scale in percentage. So basically, and what you would like to add is just the add the turbulence in the perpendicular, or yeah, in the component which is perpendicular towards the direction of the flow. Sorry. So the fluctuation scale is set in this case only in y and z direction. So there will be 10% root mean square value added to the reference field, so it doesn't change the flow rate, but it just adds the fluctuation. And alpha is called some kind of some it could be called as a relaxation, but it's not a relaxation. It's just the fraction of new random component added to the previous one. So you can basically you can model, or you can you have enhanced how the frequency of the oscillation. So less number means less frequent oscillation and larger eddies, compared to the one where you really at every time step you add new random oscillations. So you can manage the parameters by it. So it's not like it's not coming from the theory like with the given frequencies of the turbulence and etc. But it made a lot of work to really create the turbulent flow on your for your simulations, mainly for the external flows, of course. Here's a simple example. So this is a transient simulation. I think it's the LES, the same like I showed you before, without the turbulent inlet. So with the simple fixed inlet velocity, and these vortices are visualized using the Q criterion. As you will see in the next slide, I use two criterion, one higher for the showing the vortices in this half of the domain, and a lower number of Q to show you the turbulent vortices for the inlet velocity. So this is the without it, and this is how it looks with the turbulent inlet velocity, 10%, as was shown in the previous slide where the turbulent velocity inlet was presented. So you can see everywhere is the turbulences. So this is basically how the turbulent velocity inlet works. So for basic simulation with the real turbulence velocity inlet, I think it's pretty nice. So now the users has this option how to generate the turbulence from the inlet for the LES-like or DS-like models. Okay, for the LES modeling, we also need better discretization schemes for mainly both for spatial but also for temporal discretization. In the previous versions, we need to use the scripting for enabling these discretization. So now we added it to the standard options. So now you see in the solver setup, you have a special discretization and temporal discretization, where you have a list of the Euler, which is the first order implicit scheme as was default in the previous versions. And now you can choose the backward, which is the full second order scheme, but potentially unbounded. So you need to be, so everything should be smooth enough to be able to enable this backward. Or you can go for Crank-Nicolson scheme, which is a second order implicit, but it's blending between the Euler and Crank-Nicolson. So based on your geometry, based on your physics, you should choose the proper value. So 0.7 up to 0.9 is for standard industry application is okay. So now you have these options. Okay. Here's just the how it looks when you use just first order scheme and, for example, the second order scheme. So this is the again simulation of these box, and this is the simulation with the Euler scheme, and this is the simulation or the result with the Crank-Nicolson, with the Crank-Nicolson parameter equals 0.7. So you can see that the resolution and basically the temporal dissipation is much lower for the higher order schemes than for first order scheme. So you can see the importance of the discretization schemes with respect to the resolution and all the vortex shapes. So this is This is discretization schemes. Then TCAE for the acoustic, the colleagues implemented or optimized the algorithm which processes the signal. So just to quickly repeat, from the CFD simulation, you gather the information about the pressure fluctuation on some reference surface, and this reference surface data are then taken to process the acoustic, so make the acoustic analogy and propagate the acoustic signal towards the observer. And in the previous version, the algorithm needs to take all the data for all the time steps to process them, which for very fine meshes and fine reference surfaces, for example, took more than 100 gigabyte of memory. But this new algorithm, new method is much less hungry for the RAM, and the benefits are visible. So you need more or less than 10 times less RAM usage for processing the signal, and also the speed up of processing was also speed up. So new algorithm is much more efficient and more accurate because we also re-implemented some codings which makes the code even more accurate, faster, and less hungry for the memory. Okay, and I think this is almost the last one. So optimization algorithm Dakota, the ego. So efficient global optimization was added from the Dakota software, and now, so in the previous version you need to create a script which connect the Dakota and TCAE, but now it's implemented internally, and now you just it just requires to have the installation on your computer, and if it's not in the system, it's not visible in the system, you can add the path to your installation of the Dakota, and then you just run it and everything is connected together, and basically in this way you can use new optimization algorithm, this eco global optimization. You can find it on the Dakota web pages and get more details about this, but the connection now is pretty simple. And the last one is the axial blood pump. As Lubos already mentioned, we are part of a new long-term research initiative focused on biomedical flows. So we started with optimizing the blood pump, and there will be several other works. We cooperate with Technical University and Czech Academy of Science. So we put the basic geometry, and we make it available so for the users to play with this kind of application. So this is now also available on our web pages. You can find it there. And I think this is all from my side. So this was the main list of the visible new features and functionalities. And as already discussed, there were many bug fixes which are not directly visible but make the product, make TCA more robust and more efficient, more accurate. Okay, so now let's see if Lubos is still there.
Yes, yes. I'm very
Yes,
closely
he
following
is.
Radek. Of course, I am. Of course, yes. Thank you, Radek. It was, yep. Again, you did it. Yeah, pretty nice. So it was like an overview of the new features. So thank you for it. So it's back on me, I guess. Can you see my screen? Oh no, I need to say again, I am going to share it. Okay, so I'm doing it now. So
yeah, now we can see.
I'm back in the
Now
presentation.
we can see it. Yes.
So yeah, we are in the last part of our webinar. I would like to kindly ask the audience to ask your questions. We will pick the most representative and relevant questions to the topic and answer them publicly, what's possible and what we think makes sense and brings any value for the audience. And the specific questions and sensitive questions we will of course answer later via email. And this also is valid for the future questions. So feel free to ask in the future if your ideas or questions pop up later. Just come back to us and we will gladly answer them, of course. So okay, I'm going to open the box with questions now, and I can see there are some, not many. So typically, yeah, Muhammad is asking whether the recording will be available. Yes, the recording of the webinar will be later publicly available. We automatically put all our webinars on YouTube, and there will be also an email that we send to all participants about the recording link. So you can be sure that there will be a recording and you can view it in the leisure if you missed something or not had the chance to follow the whole webinar. Yep. So Radek, feel free to serve yourself with the questions. I'm taking one already. So Leopoldo, yes, hello. Well, we are coming. We promised we will come back with cameras, Radek, quick, right? So
Okay.
so we're coming back. Yes, we are here. It's us. We are humans, right? Still alive. And okay, Leopoldo, by the way, we will see together in Uruguay. We are going to Uruguay with Radek to give a training and participate in the conference. So anyone is welcome if you want to have a beer with us on Southern Hemisphere. So you're welcome next month. And yeah, Leopoldo is asking. He will be there, by the way. Could you create a module to design hydro turbines? Yes, this is actually a good question, and it's quite principled. So let me answer it. TCAE is by its default, by its origin, and by its nature, it's a simulation tool, right? So the TCAE takes the geometry and simulate it, but it's not a design tool. Not by nature. We can help to get as close as possible. We can integrate the design tools. We can even create simple design tools, or some CAD systems can be design tools, but we are not design engineers. We are a group of very efficient and smart engineers here at CFD Support, Radek, right? And we don't do design. We don't do design. So the design of the machines has to come from somewhere else for several reasons. It's the way we have chosen. But of course, I did a little research during the webinar, so I will share that I have found, for example, about hydro turbines. This guy called Beltrami, I guess it's the name of this guy. He created and made publicly available on GitHub this tool, which allows parametric creation of hydro turbines, for example, or blade turbo machinery in general. So yes, maybe in the future we will play with it, but anyone can, by the way, because it's public, it's open source, and you can take a look. You can Google it and play with it this evening. By the way, with ChatGPT, it's very efficient to play with these Python scripts, and I'm absolutely sure that you would very quickly get what you need, because it seems to be parametric. So that's just an idea, right? You can play with this, but it goes beyond our, I would say, beyond our field, and we believe that it makes sense if we do something what we know very well and where is our added value very high, which is simulations. But yes, we will be happy to help with other things. Also, we also had email correspondence with Leopoldo, so I also recommend this. For example, Rhino is really good and cheap professional CAD system. So if you haven't one yet, Rhino would be definitely a good candidate. And I know that some people use it for parametric building, parametric geometry builder for the turbo machinery. I know quite of groups who do that very successfully. By the way, the axial pump for the blood flow is also created in Rhinoceros slash rhino, sorry, slash grasshopper, and and it's very efficient, and it works, and the model is parametric. But it's a side business for us. The main business for us is definitely simulations. I hope I'm transparent in this. I hope it's understandable and clear. Oh, okay, so let's take a look what else we have here. Questions. Yes, so this one. Radek, can you see one you would like to answer?
Well, I think from Daniel is written, hello, you mentioned also improvements on command line and batch mode, right? So if I remember correctly, in the batch mode, which is connected to the Linux, we are adding some, how it's called, interactive option, or the options which automatically show you all the commands which are available,
Auto
and
completion.
auto completion of the command. So you need to go for manual every time, but if you hit the tab button, then it will show you what are the options with respect to the reading project, writing project, running project. So mainly the user friendly help
Yeah.
for typing the command by heart,
Yes.
right?
So we haven't any big news for command line. I'm sorry. Maybe we were not clear with this. But by the way, the command line is quite powerful. Just yesterday with Radek, we have found out that there are more options than we thought, right? Also the interactive option. But yeah, so yeah, command line batch mode is powerful, but we haven't any big news in this in this release for this.
Yeah.
Yes. Also, Axhai is asking why we have chosen EGO, the the global optimization algorithm. Why not other ported from Dakota? Yes, a colleague of us who's really good on this topic made a research, and he decided he made this research, and decided to use this EGO algorithm. Because it's best for the nature, or that's what we believe in. It's best for the nature of computation fluid dynamics, and probability of yeah, optimization function distribution. So yeah. So that we decided to go for ego, and the rest is not there yet. But so we have three optimization algorithms so far, and we believe it's good enough. And from Dakota, it sounded to us the most appealing to problems we solve. No
You would
special
like to
reason.
extend, right, these two options, which is the golden section search and direct, where golden section search is basically looks for the local extremum, right? The first which found is the final one, and the direct. So we equipped with some the general optimization to find a global optimum, and the ego was the best choice at the time we implemented it, right? So for application we need to cover, it was the best option at that time.
Okay. Yeah. I have to say I don't see any other relevant questions to answer at the moment. So this could be it. We also are running a little slightly over time. We scheduled this webinar for about 1 hour. So we are not going to torture you anymore, and we will stop right here. We would like to thank you for your time. We hope we will work together in the future. So feel free to ask your questions anytime in the future, and we will be happy to answer them. It's our job. It's also a pleasure. So let's keep in touch, and yeah, sometime, somewhere, see you.
Perfect.
Thank you.
Nothing
Bye
to
bye.
add. Thank you and bye bye.
Thank you. Bye bye. This would be it. Yeah. And we have to close this as well. Yes.